Okay, I can't hear you guys, but fortunately you can hear me. And someone is pointing towards the microphone. So give me a thumbs up if I can start. No? Yeah, awesome. Okay, perfect. So I can't hear you guys, but you can hear me. Great. My name is Thomas Weible, co-founder from Flex Optics. And together with my colleague Marcus, I founded Flex Optics a couple of years ago. Marcus is on site at Safnok. You might spotted him already, also wearing an orange shirt. We are specialized in optical transceivers, and today my talk is mainly about the upcoming 400 gig new technology, which comes to switches and router hardware, but especially to transceivers. And why I do this talk is formerly I was leading in the company the software development part, developing software for the Flexbox, the device which we develop. But more and more with the time, I moved towards the transceiver technology and being more specific, what kind of application in a network you can build with transceivers. And that's one part of the talk today. So coming to 400 gig, the new challenge there is to understand a little bit the background about the innards, what kind of components have been placed in such a 400 gig transceiver, especially to enable 400 gigabit. And I have to scroll down, right? Before I'm gonna start, so you should see now a new slide saying theory. I want to introduce, or I want to show some theory about the 400 gigabit technology. So what you see here on the slide, beside my head and the word theory, you see a rectangle shape of a signal. And this rectangle shape interprets a signal having two events. On the right side, you see the event of 0 and 1, and this does represent 1 bit, basically. So we got an event of 0, and we got an event of 1, and this gives us a signal. Now, why is that so important to know is some of you might have ever heard about an eye diagram. And talking to network engineers, I quite often hear, yeah, the eye diagram needs to be beautiful and nice and open eyes. But I figured out not everybody knows exactly what an eye diagram is and why it is so important. And that's the part I'm going to show now. So looking at our rectangle shape is, we have here an event, we have here two events of 0, 1, 0. A signal having 3 states, 0, 1, 0. And the rectangle shape is no longer a rectangle, it's more a sinus, as we are talking about high-speed signals. So this is actually the sinus which you see here on the screen is actually our rectangle, which I showed previously on the theory page. And having 3 different states, this gives us the possibility represent them in 8 different manners. So we got here in the top left corner 0, 1, 0, and below that we got, for example, 0, 0, 0 in a sequence, or 0, 0, 1, and somehow it doesn't like this, or 0, 1, 1. On the right side we see 1, 0, 1, and so on and so on. So we got 8 different states representing our three events basically there. So, and when we overlap them now, all of them together, when I scroll down, I have to do it like this. Oops, put that on the left side, because otherwise I think you will see that. On the bottom right corner, that's basically the overlap of our 8 different statuses, which I showed previously. And as you can now imagine, there is somehow coming an eye out, but it's not all about it. So a little bit above that, there is actually an eye diagram made of a 100 gig transceiver. And what makes an eye is this shape in the middle. And this shape is really important for an eye diagram. So we got those 2 events, 0 and 1, seeing on the right side. And we really want to make sure that the high-speed signal doesn't cross that shape in the middle, because when it would do that, the receiver on the other side couldn't detect if it's a 0 or a 1. So we need a really defined status there, either down to the bottom to 0 or up to the 1 here. So this shape makes the eye diagram actually an eye diagram. So we don't want to cross that eye. Having that sequence now of a couple of bits, as I said, we want to make sure we don't want to have dodgy eyes. Dodgy eyes can look like this. This was me trying to play ice hockey, but I wasn't so successful. But as shown at the beginning, we want open, beautiful eyes. Coming from that eye diagram, there is a new thing which you see now here. So it looks a little bit with more intermediate steps in there. So instead of having now 2 events of 0 and 1, we add two additional intermediate steps. So this signal itself has now 4 events, starting from 0, 1, 2, and 3. So we added 2 intermediate steps in the middle. And how does this look like? I will show on the next slide. This is how it will look like. I have to put that again away, put it up there. It's again an eye diagram, but from a 4-level pulse amplitude modulation. And the great thing here is now, so it's still a signal, having now 4 states. So we got here state 0, 1, 2, and 3 on the right side. And in the middle, we see 3 eyes, so it looks a little bit like a monster. The great thing now is it's the same frequency like shown previously, but we can represent now 2 bits with that signal. And that's pretty great. So we basically just doubled the amount of data we can transmit on the same frequency. And this 4-level pulse amplitude modulation, also the acronym is called PAM4, is a really important thing for 400 gigabit. And this is one of the main drivers within or enabling 400 gigabit on our lines. So far the theory, but how is this implemented now in transceivers? And that's what I'm going to show. I first want to do a recap on 100 gigabit. So opening up a the zoom is somehow a little bit bigger than on my screen. I just get rid of the headline. So, you know, it's 100 gigabit. We are talking about, so we start on the left side now. Open up a 100 gigabit transceiver. We see 2 main components in there. On the left side, you see the electrical components. So having there 4 times 25 gigabit connecting to the optical side on the right side, also with 4 times 25 gigabit. This is basically the setup of today's 100 gigabit transceivers. If we move forward towards 400 gigabit, this looks a little bit different. So first of all, as I introduced in the theory part, we have this 4-level pulse, this PAM4 modulation, which doubles our data rate. Plus now the fact on the electrical side, we just double the amount of lanes we have. And so 8 lanes doing 50 gigabits with the same frequency. So the PAM4 is now in the 50 gigabit in there, gives us 400 gigabit on the electrical side. So this electrical side is connected with 8 lanes to the optical engine, and this is also doing 8 times 50 gigabit. And this is going to be the first stage for 400 gigabit, so doing 8 times 50 gigabit in a single transceiver. But that's not the end of the road. With further developments, there will be some new components introduced in a transceiver. It's called a gearbox. I'll move that one again a little bit. So sorry that I just had to move this window thingy here, or maybe I can just do it away. Yeah, way easier. Put it up there. So Still on the electrical side, we do have, or we see 8 times 50 gigabit. And but this time it's not directly connected to the optical components within that transceiver. No, a ASIC is placed inside that transceiver. It's called a gearbox, and what it does, it takes those 8 lanes and combines it to 4 lanes, and that drives an optical engine doing 4 times 100 gigabit. And this is quite important because you want to see later on from the type of applications we can get there. There might be the question now, hey, why don't we just run 4 times 100 gigabit on the electrical side? In theory, this would be possible, but it's way cheaper to put a ASIC into that transceiver instead of having high-speed enabled 100 gigabit electrical PCB, because for such a high-speed signal, because you have to increase the frequency there basically, you need really expensive PCB material, and it's cheaper to place an ASIC inside there. And that's the reason why the multi-source agreement who defined the transceivers stick to that solution, placing on the electrical side a gearbox. Moving on there, so as I said, we opened up a transceiver. So what kind of transceivers will there be available in the future? On the top, you see a we do it like this, okay? On the top, you see a QSFP28, which is the current 100 gig solution. And in comparison there, and this is a new one, is the QSFP-DD called, or alternatively, it's an OSFP, which looks pretty much like this in comparison of the shape. So a QSFP 28 and a QSFP-DD, which you see in the top, have one big advantage. A QSFP-DD slot, so a 400 gigabit slot, is backwards compatible to a 100 gigabit QSFP28. So you have the ability to plug in a QSFP28 into a QSFP-DD slot. And how is this made? It is mainly done on the electrical side, which you see on the left. So a QSFP28 has one row of golden finger pads, which are connecting to the socket in the switch. Now a QSFP-DD slot has basically 2 rows of golden finger pads, and when you plug in a QSFP-DD, both rows are used. And when you only plug in a QSFP28, only the first row is used. And that's how this backwards compatibility is made. For the OSFP, it's a new introduced form factor. There's just one single row of connector on the backside, but it's way bigger in terms of the dimensional length and depth. The grade or the advantage of the OSFP, and that's what we see later on when it comes to the power consumption, is it has an integrated heat sink. So the OSFP has a nice capability to get rid of the heat easier compared to QSFP-DD. I also mentioned the dimensions, especially the part at the front, which sticks out of your 1U or your switch. Doesn't matter what size of the switch, but the part which sticks out of the front unit of your switch is limited to 20 millimeters or maximum 35 millimeters. There is a new definition also coming out, going up to 35 millimeters of that portion which sticks out. And why do I mention that? As I said at the beginning, I'm more also related to field application and looking how transceivers are used in the field. It is quite important to know that, because when you do the math and see the 20 millimeters of the portion of the transceiver plus 50 millimeters of your connector, of your fiber optic connector, plus a little bit, you want to give the fiber optic cable a little bit bend radius because you don't want to bend it too hard. You need at least 100 or 150 or up to 150 millimeters space in front of your first rack unit to the door, because otherwise you can't close the door any longer of the rack. And that's something which was introduced or which was shown at the first 10 gigabit DWDM SFP pluses. And we have seen the quite serious installations where the people couldn't any longer close the door. So the bad news are, be aware that you need enough room from the first rack unit or to the front door. That's really important. Now, what kind of applications are possible with the 400 gigabit, with the upcoming ones? For sure, we can do a straight connection between 400 gigabit and 400 gigabit, but it's also going to be backwards compatible to 100 gigabit. And it doesn't matter which form factor we are talking here, either QSFP-DD or OSFP as a pluggable. So both are pluggable transceivers. So we have the 400 gigabit switch on the left side, and we can connect it in to 4 times 100 gigabit on the right side. All is done on PAM4 technology. So we are speaking 100 gigabit on each lane there on the optical side. And on the others, on the 100 gigabit side, we either have 100 gigabit QSFP28 based network cards or switches. And with the time, there will be some new form factors also introduced for the 100 gigabit, which is the micro QSFP or SFP-DD, or yeah, something else. But pretty much these are the new developments on the 100 gigabit as well, and that's a result of the 400 gigabit basically. Why do I mention also the QSFP28 here? So the QSFP28s we have currently out there, they are not compatible on the optical side to the 400 gigabit. They will, because they don't do 100 gigabit on the optical side. They do 4 times 25. Now the new QSFP28s, they do on a single lambda with PAM4 technology. They will do 100 gigabit, and that's the major difference. There, and those will be available, those QSFP28s also when the QSFP-DDs will be available. So from the application point of view, that's pretty straightforward. Now, when it comes to definitions of the IEEE and in terms of link length and kind of wavelengths used, things have changed there a little bit. In the 100 gigabit, only talking about single mode now, only LR4 was defined by IEEE. So really important. I'm just talking about single mode now, not about multi-mode. So on single mode in the 100 gigabit, only LR4 technology was introduced, and this gave somehow issues because technology-wise, there were some other ways possible, like you might have heard the term CLR4 or CWDM4, using the CWDM wavelength only up to maybe 2 kilometers. For 400 gigabit, IEEE extended that now because they figured out, hey, it's really important that we introduce there more ways that people can interconnect their switches. And why do I mention that? We have seen IXPs out there which mainly stick to LR4 for 100 gigabit and didn't use any other technology because the IEEE interface didn't define it. Now, so what is now new on 400 gigabits? So first of all, there will be DR4. It's up to 500 meters, and it's a parallel single mode technology doing 4 times 100 gigabit. And that's also, that DR4 was shown in the previous slide. So that's basically the DR4 technology there. The second one, which the IEEE defined in their 802.3BS standard, is the FR4, or when we look at the beginning, it will be FR8 and then FR4, doing 4 wavelengths in the CWDM grid with a spacing of 20 nanometers up to 2 kilometers of distance. And I think that's a pretty hot and nice candidate, even like defined interfaces on an exchange point, for example, because the exchange point only defines the interface at their side. And when they say, okay, well, we follow the IEEE and it's FR4 technology based on IEEE, then you as a client you know which kind of transceiver you need to use. Up to 2 kilometers, and also LR4 will be there spacing pretty much the same like With 100 gigabit, we have a LAN WDM spacing of the wavelength inside that transceiver. So it's 5 nanometer spacing of those 4 waves going over the line, over the fiber, up to 10 kilometers. So that's the current status where we are, and where we will see in the near future the first transceivers popping up. As I mentioned, you see it down there in the bottom. It's based on that IEEE 802.3BS standard. Beside that, new plugs are coming again, and it's always a comparison with 100 gigabit. Within 100 gigabit, there was MPO12 or MPO12 two-row plug. This is a parallel plug. And now with 400 gigabit, we need at least for the multimode way, or even for the PSM solution, the DR4, we need a way to increase that. For DR4, the MPO12 is sufficient, so we have 4 lanes there, TX and RX. But when we, for example, look at multimode transmission, doing 8 lanes there with SR8 definition, it's gonna be MPO16. So 16 fibers in one plug. And Y16 for sure, we have 8 lanes, and we have 8 times TX, 8 times RX, combined gives 16 lanes. The good news is the MPO16 will have a new keying, so you can't mix it up. So you can't mix it up with the MPO12, and they won't fit each other to each other. On the single mode side, a new plug is introduced. It's called the CS plug. It looks pretty much like an LC plug, which you see on the right side. The CS plug is half the size of an LC, and we can increase the plug density on the outlet or on the receptacle. And yeah, that's basically it. I think that CS plug is pretty nice. Here again for single mode transmission. Now, power consumption. As I said at the beginning, power introduced with the OSFP is that this integrated heatsink is important. And why do I mention that is when we put power in a transceiver, we also want to get rid of that power in terms of heat. And this is somehow also a lesson learned from 100 gigabit. Looking at the QSFP28 definition, it can take up to 6 or 7 watts of power, and also can have a heat dissipation of 6 or 7 watts. But this gives us also a limiting factor of latest of newer technologies. And for example, when we're talking about DWDM or coherent solutions, doing more than 10 kilometers, going up to maybe 80 kilometers. And this lesson was also learned for 400 gigabit, that the power definitions went up for up to 15 watts of the OSFP. And for the QSFP DD, we are currently at 12 watts, but there are some trials already driving that QSFP DD up to 15 watts. And these figures are really important to know, because when you imagine you have a 1U switch with 32 ports, 400 gigabit, this will end up just on the optical side with roughly 500 watts just for the transceivers, first of all in power consumption and then of heat dissipation. Now, taking in consideration that the switch is not only existing out of transceivers, but also has memory and power supplies and the CPU and the ASICs in there, they also consume power. We might end up with a 1U switch doing 400 gigabit with 32 ports running at 1 kilowatt of power and also generating 1 kilowatt of heat. And that's quite a massive amount. As I said, it's the drawback is the huge power consumption, but it also, and the benefit is what we get out there is that we get rid of that power in terms of heat dissipation. And there were some really smart things were made for the OSFP and QSFP DD there. I already mentioned like things like coherent DWDM. So why is it so critical, and why, for example, do we see that for QSFP28 having a coherent solution there yet? Is there is an additional chip placed there called a DSP, digital signal processor, and they just need power, and that is power and generates heat, and that's an important component to enable, for example, coherent solutions. And when yeah, that's basically for that. And if people are asking me, hey, what are you gonna see now in the future? Is it gonna be more OSFP or QSFP-DD? That's a tricky question in terms of the form factor. For sure, the OSFP, as it's a little bit bigger and size is really a critical component for power consumption or heat dissipation. In a pluggable module, because that's really important to know. We are always talking about pluggable modules, but the OSFP will be one of the first being out there on the market, and I'm pretty sure we will see the first switches coming up by the end of this year, being public available. For example, Arista, they are jumping on the OSFP at the moment. For the future, I think the QSFP-DD will be a little bit ahead, because it's just backwards compatible to QSFP28. And that's also what Arista sees in terms, because they already introduced an OSFP to QSFP28. That's what I saw. And I'm pretty sure they also will introduce a QSFP-DD converter. So it's a component where you can plug in a QSFP-DD into an OSFP. It's an adapter. So in the long run, pretty sure the QSFP-DD will be the one where more vendors will jump on it, and which gives you more flexibility. From the programming perspective, that's where we are coming from. I'm pretty sure there will be pretty much a lot of tasks to do also for programming those transceivers. We have seen that with QSFP28. For example, when the first ER4s, so doing 40 kilometers on 100 gigabit were introduced, they were not recognized at all by the legacy layer 2 or layer 3 gear. So we started to change that configuration and basically told that switch, hey, you got an LR4 transceiver in there, although it was an ER4, and suddenly it enabled that port, and the customer was quite happy to light up his fiber up to 40 kilometers, although it was never intended to do so, because the definition was up to 10 kilometers, because only LR4 technology was supported. So, and I'm pretty sure we will see similar things for QSFP-DD and OSFP there as well. This brings me to the end of my presentation. Thank you very much for listening, and I'm gonna swap now again to the camera, because then I can see the audience if there are questions about the 400 gig technology. Thank you very much. I see the clapping, but I don't hear it. So I might get over to the chat. Okay. Mark just mentioned he will type in the questions. So I wait for the questions.